I'm Lucas Schell, and I'm responsible for the course block on alignments. I will here today mostly focus on pairwise alignments, namely sequence alignments of two different sequences. And this is in opposition of, for instance, multiple sequence alignments where we are aligning more than two sequences. So first off though, what is a sequence alignment? Here is a trivial example of a pairwise sequence alignment. In this case, we have placed two different sequences, GATTA on top of GCTAC. And we have arranged them in such a manner that we, by some criteria, obtain an optimal resemblance between the two sequences in each position. In this case here we have firstly sequence positions like this G here and the T and the A, where we have a match between the upper and the lower sequences. These positions are called matches. We have as well have examples of so-called mismatches, and that's for the A and C here, for instance. They are not the same character and hence are differing. We as well use a structure that we call deletions, and that's when one of the sequences don't have a sequence letter at a given position, and we as well have inserts, and that's when the same thing is true for the first sequence. So with these structures, matches, mismatches, inserts and deletes, these are the operational blocks that we use. We use sequence alignments when we want to find both similarities and differences between sequences. The differences are useful, for instance, when we want to find sequence variants like SNPs, or if we want to determine evolutionary relationships between known related sequences. This is normally as an input to, for instance, phylogeny. You can as well use it when the opposite way, when you want to find the similarities between different sequences. For instance, if you want to determine regions of sequence conservations. This is often related to the function of a sequence. So, for instance, in protein sequences, we often look for conserved regions because they're more likely to contain the functional elements of the protein sequence. And as well, if you want to retrieve homologs from databases, we would like to find all the sequences that look like the sequence that we want to query or what. So actually you see sequence alignments quite frequently in all kind of occasions. For instance, when we want to determine the origin of different COVID strains, the reason why we can say that a certain COVID strain is more similar than another is that we look on the sequence conservation between different individuals. As well, if in forensics, for instance, when we want to retrieve individuals that are similar to the suspect, if we're using sequence information, it's actually alignments we use to find out whether two sequences are related or not. There are multiple ways to form alignments with the same two sequences. We can actually shift them around quite a bit and still make different alignments that make sense. And there's often various opinions about what makes a good alignment. However, in order to make things more stringent, it's useful to define what we know as a scoring function. So this scores any two letters in an alignment that sit on top of each other. So and you would then there are many different variants of this, but one typical scoring function could be that if the letters are the same, then you give a match score for this position. If there's sort of a gap in one of the two, so if you see either an insert or delete in this position, then you give this position a gap penalty. And if there's sort of not a match in the position, or and not a gap or delete or any kind of gap, then you have a mismatch, and you set yet another score for that. So here I take an example for the these two sequences, GATA and GCTAC. If we arrange them with a gap between the T and A of the second sequence and a gap in after the last letter in the first sequence, then we would see that there's firstly a match followed by a mismatch, followed by match, followed by gap, followed by match, followed by a gap. And this would render a score of 2, 0, 2, 1, -1, 2, -1. If you sum that up, we will get a score of 4. And this would then sort of be a better alignment according to this scoring function than, say, for instance, the next alignment here, where we have kept the sequences intact but just shifted in one position to each other, and then we get a gap in the first position, a mismatch, a mismatch, a match, a match, a gap. So that's now 4 for the two matches, and we will have to withdraw -2 for the two gaps, and that renders a score of 2. So having a scoring function allows us now to compare the two different alignments and see which one is the better one of the two. Given such a method to compare the two different alignments, we can of course try to find the best alignment out of all alignments. It's however not that easy to do so, just because the computational complexity of this. I will just try to illustrate what I mean by this. So imagine now that you have two different sequences, the same one as we had before here, and we want to find the best possible way to align these two sequences. We could imagine that we now build an algorithm that would compare firstly this alignment here that I have, and now compare that to if we have 1 insert at the beginning, 2 inserts at the beginning, 3 inserts at the beginning, 4 inserts at the beginning, and then for each of these positions we could calculate an alignment score and then select the best one. However, it becomes quite a number of different comparisons that we have to make, because it's actually not just in the beginning. In the beginning we have a possibility to insert gaps, but it's as well as in all the other positions as well. So we sort of have to start to move and introduce gaps in all various different positions. So and we could sort of do this in a systematic manner like this, and we would realize that actually even when we have finished all these, we then have to start to look on the next, on other permutations, such as something like this, and we could now start to shift through all these different positions, and eventually we might be able to find something that would be optimal. However, to not having to exhaust ourselves, we will instead have a much more efficient way to find this, and this will be covered in the next lecture.